In today's lesson, we're going to learn how to solve systems of equations using three methods: graphing, substitution, and elimination. So this is an example of a system of equations. A system of equations just means you have a set of two or more equations. In order for an ordered pair like this to be a solution to a system of equations, the ordered pair must give you a true statement when it is plugged into all of the equations within your system. So let's check to see if this ordered pair is a solution. So I've copied down this first equation, and then I plugged in -3 for x and 4 for y. And if we simplify, this will leave us with -3 minus 8 is equal to -11, and -3 minus 8 gives us -11. So when we plug this ordered pair into this equation, we get a true statement. -11 is equal to -11. That's true. But in order for this ordered pair to be a solution to this whole system, it must also give us a true statement when we plug it into this bottom equation. So I went ahead and copied down this bottom equation and then plugged in -3 for x and 4 for y. And let's see if we get a true statement. When we simplify, we get the statement -1 equals -1, which is definitely a true statement. So we can say that this ordered pair, -3, 4, is a solution to this system of equations because it satisfies both equations. Let's take a look at another example. So I went ahead and copied down this first equation and plugged in -5 for x and 3 for y. And let's go ahead and simplify. We get the true statement, -11 is equal to -11. So this ordered pair satisfies this top equation. But again, in order to be a solution to the system, that ordered pair must satisfy both. So let's plug this ordered pair into the bottom equation. Now we ended up with a false statement. -9 does not equal -1. So since this ordered pair does not satisfy all of the equations in our system, we would say that that ordered pair is not a solution. Next, we're going to discuss how to solve a system of linear equations by graphing. When solving a system of two linear equations by graphing, the solution is the point or points of intersection, if any, of the two lines. And there are three different possible solutions. The first solution is that your lines might intersect at one point. In that case, the number of solutions to that system will be 1, and the way we write our solution is as an ordered pair. For example, let's suppose these two lines intersected at the ordered pair 2, 5. The ordered pair 2, 5 would be our solution. Another possibility is that when you graph your two lines, they are parallel. Remember that parallel lines never intersect. Since the solution is the intersection point of your two lines, if your lines are parallel, that means that the number of solutions is none, since there are no intersection points. And the way that we would write our solution could be to use this no solution symbol, or we could write out the words no solution, or use the words empty set, or we could say that this is an inconsistent system. The last possibility is that when you graph your two lines, let's say your first line is y equals -2x plus 1, and when you graph it, it looks like this. And then let's suppose your second line, in this case 4x plus 2y equals 2, coincides perfectly with your first line. Remember, the intersection points are our solution. Since these two lines are identical lines, they intersect at every single point along the line. So there are infinitely many solutions. And the way we write our solutions for systems that have infinitely many solutions is using set builder notation. We start with this general outline, and then you can insert either equation into this blank. Here I've written this purple equation in the blank. Another correct way we could write the solution would be to instead insert this equation in the blank. Again, these two equations represent the same exact line, so it doesn't matter which equation you use in your answer. What does this answer mean? Well, remember, the solution is the point or points of intersection. These two lines intersect at every single point on the line since the lines coincide perfectly. Well, that's just what this says. This says that the solution is the set of all ordered pairs that lie on the line. Now that we've discussed the different possibilities for our solutions, let's take a look at some examples of how to solve system of equations by graphing. Let's first solve this system of equations by graphing. And I'm going to label this equation A and this equation B. Let's start by graphing equation A. Equation A is already written in y equals mx plus b form. So we can see that the y-intercept is 4. Let's plot the y-intercept on the y-axis. And the slope is -2, which can be written as -2/1. So let's go to our y-intercept and let's use the slope to plot the next point. Let's go down 2 and to the right 1. Now we only need 2 points to graph a line, but I'm going to plot a few more points. I'm going to continue moving down 2 and to the right 1. And now I'm going to draw a line through those points, and that gives us this line here, which I'm again going to label A, just to help distinguish between our two different lines. Next, I've copied down equation B right here. Now, equation B is not written in y equals mx plus b form. To graph it, let's go ahead and rewrite it in y equals mx plus b form. And to do that, we need to isolate y. So I've succeeded in isolating y, and now our equation is rewritten in y equals mx plus b form. Now in order to graph, first let's identify the y-intercept. The y-intercept is -2, so we'll find -2 on the y-axis. Now let's identify our slope. The slope is 4, which I've rewritten as 4/1. So we started our y-intercept, and we'll use the slope to plot an additional point. We'll count up 4 and to the right 1. And I'm going to label this line, line B. Now remember, this is a system of equations, and when you solve a system of equations by graphing, you're looking for the intersection point. It looks like our two lines intersect right here, so the ordered pair of this intersection point is our solution. It looks like that ordered pair has the coordinates 1, 2. This is the ordered pair that satisfies both equations. You could check your answer by plugging in 1 for x and 2 for y into this equation and making sure you get a true statement, and then plugging it into this equation and making sure you also get a true statement. Let's take a look at another example where we solve a system of equations by graphing. Now, to find the solution, we want to graph these two lines, and the solution will be their intersection point. To start, I've copied down equation A. And in order to graph this line, let's write the line in y equals mx plus b form. And to do that, we want to isolate y on the left side of the equation. Now that we've written our line in y equals mx plus b form, we'll start by identifying and plotting the y-intercept. The y-intercept is 5, so we'll find 5 on the y-axis, and we'll plot that y-intercept, and the slope is 1/3. So starting at our y-intercept, we'll plot the next point by counting up 1 and to the right 3. And then we can go ahead and draw a straight line through our points. Next, we want to graph line B. And in order to graph line B, we need to write the line in y equals mx plus b form. Now for y equals mx plus b form, we want to have y isolated on the left, just like we did up here. Let's start by adding 6y. That will leave us with -2x plus 6y is equal to, these will cancel and we'll be left with -24. Now we have y on the left. Now we can proceed to isolate that y. And now we have our line written in y equals mx plus b form. Now let's go ahead and graph this line. To start, the y-intercept is -4, so we'll find -4 on the y-axis. And the slope is 1/3. So starting at the y-intercept, we'll use the slope to count our next point by counting up 1 and to the right 3. Now, notice these two lines are parallel. We can even see that by looking at the equations, because the equations have the same slope, and parallel lines always have the same slope. Now, when you're looking for the solution for a system of equations by graphing, you're looking for the intersection point of your two lines. Parallel lines never intersect. So since there is no intersection point, that means that there is no solution. In other words, there is no ordered pair that would simultaneously satisfy both equations. For problems where there is no solution, you can either write out the words "no solution," or here are some other correct ways to write your final answer when there is no solution. Let's take a look at one last example of how to solve a system of equations by graphing. Again, in order to solve this system of equations by graphing, we want to graph these two lines and look for the intersection point. And to graph line A, let's go ahead and write it in y equals mx plus b form. Okay, so now that we've written it in y equals mx plus b form, we can see that the y-intercept is -4, and the slope is -2, which I've written as -2/1. So we'll start at our y-intercept, and then we'll count down 2 and to the right 1. Next, let's go ahead and graph line B. And in order to graph line B, we need to write it in y equals mx plus b form. We need to isolate y. So we need to get rid of this term as well as this term. So I'm going to start by subtracting the 6x. And then I'm also going to subtract away the 12. These will cancel and these will cancel to leave us with 3y is equal to -6x minus 12. And the last step to isolate y will be to divide by 3. Now, let's go ahead and graph line B. Notice the y-intercept is -4, which is the exact same y-intercept as our first equation, and the slope is -2/1, which is the exact same slope of our first equation. In fact, notice the y equals mx plus b forms are identical. So when we graph line B, it will coincide perfectly with line A. Both of these equations represent the same exact line. So when you're looking for the solution to a system of equations, the solution is the intersection points. Well, these two lines intersect at every single point on the line. And since there are infinitely many points along any line, that means there are infinitely many intersection points. And the way we write our solution for problems like this, where you have infinitely many intersection points, is we use set builder notation. We start with this general set builder outline, and then we want to insert the equation for the line in this blank here. We have several different options. We could insert equation A in the blank here, or instead we could have inserted equation B in the blank, or there's even a third option. We could have inserted the y equals mx plus b form into this blank. Now, you do not have to write all of these answers. Any one of these for your final answer will be acceptable. Because remember, all of these equations represent the same exact line, this line right here. So these are all equivalent ways to write your answer. Now, for this type of problem, why do we write our answer in this form? A very common mistake is that for problems like this, for their final solution, students will write the words infinitely many solutions. But that answer is not correct, because while there are infinitely many points along this line, we want to be careful to be very specific about our solution, because not any ordered pair is a solution to this system. For example, any ordered pairs outside of the line are not solutions to this system. The only solutions to this system are the infinitely many points along this line. So this notation says exactly that. This notation says that the solution to this system of equations is the set of all ordered pairs that lie on this line. Now, when we're solving a system of equations by graphing, the solution is the intersection point of your two lines. Graphing is a nice visual way to find your answer, but let's suppose that intersection point was a terribly ugly decimal like we see here. If your solution is a decimal or a fraction, anything other than a whole number, it can be difficult to solve it by graphing, especially if you're just graphing by hand. So this is why it's helpful to have other algebraic methods for solving system of equations. So let's take a look at how to solve a system of equations using substitution. I've typed out the steps that we'll be using right here, and we'll follow each of these steps one by one. I've labeled my equations A and B just to help us keep organized. Now for the first step, we want to pick either equation and isolate one of the variables. Now for the first step, we have a lot of flexibility here. You could pick equation A and you could isolate x, or you could isolate y. Or you could pick equation B and you could isolate x, or you could isolate y. Any of those options will work, but it will be easiest to isolate a variable if it has a coefficient of 1. So if you notice that any of your variables have a coefficient of 1, I recommend picking that variable to isolate. So I see that the x in equation A has a coefficient of 1. So for step 1, I'm going to pick equation A and isolate x. But if you prefer, you could isolate y in equation A, or you could isolate either x or y in equation B. All of those ways will get you the correct answer in the end. So I've started by copying down equation A, and since x has a coefficient of 1, it's going to be very quick to isolate. All we have to do is subtract away the 1/3 y. And that will leave us with x is equal to 3 minus 1/3 y. So we've successfully isolated x. Now we can move on to step 2. For step 2, we substitute the expression from step 1 into the other equation. For step 1, we used equation A. In step 2, you want to use the other equation. So in step 2, we're going to use equation B. So I've started by copying down equation B. Now in step 1, we isolated x. And we found that x is equal to this quantity right here. So in step 2, we're going to plug this quantity in for x into equation B. So we know that x is equal to this quantity, so we're going to plug this quantity in for x right here. That will leave us with -2, and instead of x, we're going to write 3 minus 1/3 y, and then we'll bring down the minus 4y, and the equals 14. So I've copied down this exact equation right here. The only change I've made is that I've replaced x with this quantity right here. Now we have an equation involving only one variable, y in this case. So now we want to go ahead and solve this equation for y. To start, let's distribute that -2. -2 times 3 will give us -6, and -2 times -1/3 y, we could picture this -2 as a -2 over 1. And when we multiply fractions, you just multiply the numerators. So -2 times a -1 will give us a +2. And if we multiply the denominators, 1 times 3 will give us 3. And then we'll bring down the -4y, and the equals 14. Now, let's combine these like terms. And to combine these like terms, we just need to take 2/3 minus 4, which you can either do by hand by getting a common denominator, or you could punch that into your calculator. Either way, 2/3 minus 4 gives us a -10/3. And then we'll bring down the -6, and the equals 14. Now, we want to solve for y, so let's add 6 to both sides. And that will leave us with -10/3 y is equal to 20. Now, to isolate y, one option is we could divide both sides by -10/3, but instead of dividing by a fraction, I'm going to multiply by the reciprocal. So to find the reciprocal of -10/3, we just flip it, and that will give us -3/10. So we'll take -3/10 times the -10/3 y. And then if we multiply this side by -3/10, we have to multiply the other side by -3/10. When we multiply two reciprocals, we get 1, so this leaves us with 1y, or y. And if we multiply these numbers by hand, we could picture this as 20 over 1. And then if we multiply the numerators, -3 times 20 will give us a -60, and 10 times 1 will give us 10. And that will simplify to y is equal to -6. So we found y, but when we're solving a system of equations, we need to find y and x. So for step 3, let's go ahead and plug y into either of these original equations to find x. So it doesn't matter which original equation you use. I'm just going to pick equation A, and we'll plug in -6 for y. And now let's solve for x. 1/3 times -6 will give us a -2, so we'll be left with x minus 2 is equal to 3. And then we'll add 2 to both sides, and that will leave us with x is equal to 5. So now we found our x and our y coordinate, and we can write our answer as an ordered pair, where the x coordinate is 5 and the y coordinate is -6. And you could very quickly check your final answer, especially if you use your calculator. Just plug in 5 for x and -6 for y into this equation and make sure you get 3. And then plug in 5 for x and -6 for y into this equation and make sure you get 14. Now, we could have also solved this system of equations by graphing. If we were to graph, we would find that these two lines intersect at the ordered pair 5, -6. Graphing and substitution are just two different ways to solve systems of equations. Let's take a look at another example where we're solving a system of equations using substitution. When you're solving by substitution, for the first step, you can pick either equation and isolate either variable. If we look back at the previous problem that we just solved, remember for step 1, when you're picking a variable to isolate, if you find a variable that has a coefficient of 1, like this x, that variable will be the easiest to isolate. But for this particular problem, all of the variables have a coefficient other than 1. So there's no variable that will be easier to isolate in this case. So it really doesn't matter which of these variables you pick to isolate. So I'm going to randomly decide to pick equation A and to isolate y. But again, if you prefer to isolate x in equation A or either x or y in equation B, all of those approaches will get you to the correct answer in the end. So I've started by copying down equation A, and if we want to isolate y, that means we have to get this y all by itself. So now we've successfully isolated y. Now we can move on to step 2. Now, in step 1, we used equation A. In step 2, we want to use the other equation. So in step 2, we're going to substitute y into equation B. So I've started by copying down equation B. Now, we determined that y is equal to this quantity here. So we're going to take this quantity and plug it in for y right here. Now we have an equation involving only one variable, x in this case. So now we can go ahead and solve this equation for x. I'll bring down the 6x. And then let's go ahead and distribute. If you take 2 times -3/2 x, either by hand or on your calculator, that will give you -3x. And 2 times 2 will give us a +4. And then we'll bring down the 5. And now we can combine like terms and proceed to solve for x. And we find that x is equal to 1/3. Now remember, for these equations, we need to find two variables, x and y. So we're going to plug x into either of the original equations to find y. So you can pick either of the equations, doesn't matter which one. I'm just going to pick equation A. So I went ahead and plugged in 1/3 for x. Now let's go ahead and isolate, or in other words, solve for y. And we get that y is equal to 3/2. So let's write our final answer as an ordered pair, Our x-coordinate is 1/3, and our y-coordinate is 3/2. Next, let's take a look at how to solve two problems using substitution, where the answer is either no solution or infinitely many solutions. For this problem here, for step 1, we can pick either equation and isolate either x or y. So I notice here the y has a coefficient of 1, so that will be the easiest to isolate. So for step 1, let's pick equation b and isolate y. And to isolate y, all we'll need to do is add 3x to both sides. And now we've successfully isolated y. Now, in step 1, we used equation b, so in step 2, we want to use the other equation. So we're going to substitute y into equation a. So I've started by copying down equation a. Now, in step 1, we found that y is equal to this quantity right here. So let's go ahead and plug this quantity in for y into equation a. After we replace y with this quantity 3x plus 2, that leaves us with this expression right here. Now we've got an expression involving only x, so let's go ahead and solve this expression for x. Now notice something interesting happens here. 6x minus 6x gives us 0x, or 0. So we're left with -4 is equal to 1. This is a false statement, right? -4 does not equal 1. So when you're solving an equation, if you end up with a false statement, that means that there is no solution. So for our final answer, we can write no solution, or we can write our answer using any of these other ways. Now, we solved this using substitution, but let's imagine that we were asked to solve this by graphing. If you were to graph these two lines would be parallel, so they would never intersect, and so by graphing we would get the same solution, no solution. Let's take a look at the next example. In step 1, we want to pick either equation and isolate either variable. X here has a coefficient of 1, so this x is going to be the easiest to isolate. So let's pick equation b and isolate x. So now that we've isolated x, we can move on to step 2. And since in step 1 we used equation b, in step 2 we're going to use equation a. And we're going to substitute x into equation a. So I've started by copying down equation a. Now we know that x is equal to this quantity, so we're going to substitute this quantity in for x. So I went ahead and replaced x with 5y minus 3. Now we've got an equation involving only y, so let's go ahead and solve this equation for y. Now something interesting happens here. Notice -15y plus 15y gives us 0y, or 0. So we're just left with 9 equals 9. So we're left with a true statement here. And when you try to solve an equation, if you end up with a true statement, that means there are infinitely many solutions. But remember, for our final answer, we do not write infinitely many solutions, because that's not specific enough. If we were to graph these two lines, line A would look something like this, and line B would coincide perfectly with line A. They are the same line. And remember, when you solve a problem by graphing, you're looking for the intersection point of your two lines. Since these two lines coincide perfectly, they intersected all of the infinitely many points along the line. So for our final answer, we want to say that the solution, or the intersection points, are all of the points on the line. And we can write that using set builder notation. We start with this general outline, and then we can either insert equation A into the blank and write our final answer like this, or another way to write our final answer is to again start with the set builder notation, but instead write equation B in the blank. You do not have to write both of these answers, just one or the other, because remember, these are saying the exact same thing. The blue and the green line are the same exact line. And this says that the solution is the set of all ordered pairs that lie on the line. which is exactly what we want to say. The intersection points, or the solutions, are all of the ordered pairs along the line. Now, we've learned how to solve systems of equations by graphing and by using substitution. The last step is we're going to learn how to solve systems of equations using elimination, and we'll follow these steps one by one. For step 1, we need to write both of our equations in standard form. Standard form means that you have your x term first and your y term second on the left side of the equal sign, and then on the right side of the equal sign you have your constant. So to get equation A in standard form, we need to have the x and y terms on the left and the constant on the right. It looks like we'll need to move this y term to the left side of the equal sign. So let's subtract 3y, and that will leave us with the standard form 3x minus 3y. Now this equation is written in standard form. We have the x term first, then the y term on the left side of the equal sign, and on the right side of the equal sign we have the constant. Equation B is already written in standard form. We have the x and the y term on the left and the constant on the right. So I'm just going to copy equation B over here. Now we've completed step 1. Now the goal for step 2 is to get either the coefficients of the x's to be matching but opposite, or to get the coefficients of the y's to be matching but opposite. So I'm going to start by copying down these two equations into step 2. Now, in order to get the coefficients of either the x's or the y's to be matching but opposite, we want to multiply one or both equations by some number. Now there's more than one way to do this, but one option is we could multiply this bottom equation by -3, because then the x's will be matching but opposite. We'll have positive 3x and negative 3x. So let's go ahead and carry over this first equation as is, and then we're going to multiply this entire bottom equation by -3. That will give us negative 3x minus 6y. And if we take -3 times -8/3, that will give us a positive 8. Now, we've succeeded in step 2. In step 2, we wanted to get either the x's to have matching but opposite coefficients or the y's to have matching but opposite coefficients. And we've done that. We've got the x's to have matching but opposite coefficients. We have 3x and -3x. For step 3, we're going to add these two equations together. And step 3 is why this method is called elimination. Because in step 3, when you add your equations together, one of your variables will be eliminated, and that will be the x in this case. Since our x's have matching but opposite coefficients, 3x plus -3x cancels out. Then, if we take -3y plus -6y, that will give us a -9y, and 5 plus 8 will give us 13. Now, we've almost found y. So let's go ahead and divide both sides by -9, and then we'll have our y. These -9's will cancel, and we'll be left with y is equal to -13/9. Now we found one variable, y in this case. So for step 3, we're going to plug y into either of the original equations to find x. And technically you could plug y into this equation, or one of the equations written in standard form. Any of them will work. I'm going to go ahead and plug y into the original equation A. So I've copied down equation A, and I'm going to go ahead and plug in -13/9 for y. And now let's solve for x. We'll start by bringing down the 3x. And if you take 3 times -13/9, that will give you -13/3. And then if you take -13/3 plus 5, that will give us 2/3. And then for the last step, to isolate x, we could do this two ways. We could either divide both sides by 3, and especially using a calculator, that would be pretty quick. But if you're doing this by hand, dividing both sides by 3 can be a little tricky because you'll end up with 2/3 divided by 3. So another way to isolate x would be, instead of dividing by 3, we could multiply by 1/3. And I'm going to take that approach. Multiplying two reciprocals gives you 1, so 1/3 times 3 gives us 1x, or x. Let's see, if we multiply the numerators, that'll give us 2, and multiply the denominators, that will give us 9. So we can see that x is equal to 2/9. Now let's write our final answer as an ordered pair. Our x-coordinate is 2/9, and our y-coordinate is -13/9. And again, there are multiple different ways to solve this problem. You could solve this problem by graphing, although that might be tricky since our intersection point involves fractions. You could also solve this problem using substitution, and you'd get the same exact answer, or elimination works as we just saw here. Let's try another example where we're solving using elimination. For step 1, we want to write both equations in standard form. So to get equation A in standard form, we want x and y on the left. So let's add 2x, and then we can write our equation in standard form. Now, to get equation B in standard form, we need to move this constant to the right. And now we can write equation B in the standard form. Now that we've written our equations in standard form, let's move on to step 2. The goal for step 2 is to get either the coefficients of the x's to match but be opposite, or to get the coefficients of the y's to match but be opposite. There are multiple different ways to do this, but let's look at 2 different options we have here. For the first option, let's work to get the x's to have matching but opposite coefficients. So I'll start by copying down equations A and B. Now, there are many different ways we could get the x's to have matching but opposite coefficients. But one option is we could multiply this top equation by -3. That would give us -6x, and then we could multiply the bottom equation by +2 to give us +6x. Another option is instead we could multiply the top equation by +3 and the bottom equation by -2. That would work as well. So let's see, if we multiply the top equation by -3, that will leave us with -6x plus 12y is equal to -3 times 24, which gives us a -72. Then if we multiply the bottom equation by 2, that will give us 6x plus 10y is equal to 6. So we've got the x's to have matching but opposite coefficients, -6 and +6. Step 3 is to add our equations together. When we add the equations together, the x's cancel, and we're left with 12y plus 10y, which gives us 22y, and -72 plus 6 will give us a -66. Now we can solve for y by dividing both sides by 22, and that will leave us with y is equal to -3. Now we found y, so for step 4, we want to plug y into either of the original equations to find x. So I'm going to go ahead and plug y into equation A. And now that I've plugged in -3 in for y into equation A, I'm going to proceed to solve for x. And we end up with x is equal to 6. So we've now solved the problem. We found x and y. But before we move on, let's take a look at a second possible way we could have solved this problem. For step 2, instead of getting the x's to have matching but opposite coefficients, we could get the y's to have matching but opposite coefficients. So I'm going to start by copying down these 2 equations. Now there are many different ways we could get the y's to have matching but opposite coefficients. But one trick you can use here. Notice to get the x's to have matching but opposite coefficients, we took this term and multiplied it by the coefficient of this x, which was 3. And then we took this term and multiplied it by the coefficient of this x, which was 2. And then you'll have to decide if you need to add a negative to one in order to make them opposites. We added a negative here, so we would have -6x and +6x. So if we want the y's to be matching but opposite, one trick we could use is we could multiply this equation by the coefficient of this y, which is 5, and then multiply this equation by the coefficient of this y, which is 4. I would start out with positive numbers here and then look to see if you need to make one negative. Let's see, 5 times -4 will give us a -20y, and 4 times 5 will give us a +20y. So it looks like we have matching but opposite coefficients on our y's, so we do not need to make one of these negative. And let's go ahead and multiply this entire equation by 5, and then we'll multiply this entire bottom equation by 4. Now we've succeeded. Our y's have matching but opposite coefficients. For step 3, we add our equations together. Now, to solve for x, let's divide both sides by 22. Now we found x. Now we can plug x into either of the original equations to find y. So I'm going to go ahead and plug in 6 in for x into equation A, and now I'll proceed to solve for y. And we find that y is equal to -3. Notice we did this problem 2 different ways. Both ways we found that x is 6 and that y is -3. Let's go ahead and write our final answer. For our last 2 problems, we will see how to solve problems using elimination, where we end up with either no solution or infinitely many solutions for our answer. When we're solving using elimination, for step 1, we need to write our equations in standard form. To write equation A in standard form, let's go ahead and add 5x. That will leave us with, and it looks like equation B is already written in standard form. For step 2, we want either the coefficients of the x's to match but be opposite, or the coefficients of the y's to match but be opposite. I'm going to start by copying down these 2 equations into step 2. Let's suppose we wanted to get the y's to have matching but opposite coefficients. Well, we can multiply this equation by 4, and then we would have -4y and +4y. Now, if we multiply this top equation by 4 times 5x will give us 20x. 4 times -y will give us -4y, and 4 times 3 will give us 12. And then let's bring over this bottom equation. Now, we've succeeded. The y's have matching but opposite coefficients, but something interesting happened. The x's also, coincidentally, have matching but opposite coefficients. So let's see what happens in step 3. In step 3, we add the equations together. The x's cancel, and the y's cancel, so we're left with 0 is equal to 12 plus 4 will give us 16. Now, depending on what you did in step 2, in step 3 you might end up with a different answer, but no matter how you complete step 2, in step 3 you should end up with some sort of false statement. And in math, when we end up with a false statement, for our final answer, we can write no solution, or we can write our answer in any of these different ways. Let's take a look at one last example. And again, you can solve any system of equations by graphing, by using substitution, or by using elimination, but we're going to continue practicing elimination for this problem. For step 1, these 2 equations are already perfectly written in standard form. For step 2, I'm going to start by copying down our equations in standard form. Now, for step 2, let's suppose that we want the coefficients of the x's to match but be opposite. One way to do that, we could multiply this equation by the coefficient of this x, and I'm just going to write a +5 for now. And then we can multiply this equation by the coefficient of this x, which is 2. And again, I like to start with positive numbers here, and then let's see if we need to make one of these negative. Let's see, this would give us 10x, and this would give us -10x. So it looks like we have matching but opposite coefficients. So we do not need to make either of these negative. Now, if we multiply this top equation by 5, and then if we multiply this bottom equation by 2, now we've succeeded in getting the x's to have matching but opposite coefficients. But again, something interesting happened here. Again, the y's also have matching but opposite coefficients. So let's see what happens in step 3. Now in step 3, the x's cancel and the y's also cancel. So we end up with 0 on the left. And on the right, 30 plus -30 gives us 0. So we end up with 0 equals 0, which is a true statement. When you're solving an equation, if you end up with a true statement, that means there are infinitely many solutions. So for our final answer, when there are infinitely many solutions, we start with this set builder notation, and then we can either insert equation A into the blank, or a different correct way to write our final answer would be instead to insert equation B in the blank. Either one of these answers would be correct for your final answer.